All right, guys, so this is a pretty loaded word, Tritium, right? What does it mean? What is it, right? Last year it was the trust update, a new GUI. Now you've seen the Tritium white paper, you've seen a lot of what it's quantified and what it's become. So what Tritium is the foundation. It's the base layer because essentially, as you've seen what Dino's doing, he's working on layer 3. Now that's important to know because you are always limited by your bottom layer. You guys probably remember dial-up. It's because you have a slow physical layer. Everything else on top of it is built. So if you don't understand your proper foundations, then the system's never going to scale. And if you don't build the foundation properly, then you're always going to kind of have a building that's kind of an upside-down pyramid. And what's going to happen is eventually it implodes. So the initial architecture of the blockchains are kind of in the proof of concept phase. So just a little bit brief of an introduction. The biggest thing that a blockchain does, cipher blockchaining has been around since the 70s. People have understood about digital currencies. This was the first successful implementation of it because it solved what's called the Byzantine generals problem, which basically means you have two generals, General A, General B. Now, how do you make sure that a message can be communicated where they may not even have direct connection and where one of them could be malicious? And how do you coordinate an attack if they were to attack a city? And it's a long-known problem in computer science. So the fundamental way that this was solved is through a mathematical verification process where you have some sort of mathematical proof. And this mathematical proof is what gives you that ability to verify that this person has an honest answer. And this proof, blockchain, is through proof of work. Other people use proof of stake, so on and so forth. So as you know from last year's speech, it was about the three-dimensional chain. And that's an initial architecture. And now what I'm going to do is I'm going to be showing how the three-dimensional chain overlays and connects in with the Tritium software stack. So as we can see over here, we have the stack. Right? With Nexus, our stack is network, ledger, register, operation, API, logical, application. Now, why do we want a stack? I'll get to that in a minute. But this is how it connects directly in. So the network as we know it right now has the OSI network stack. That's been developed as a standardization network. So physical layer is your copper and your fiber. The data link layer is usually your Ethernet that handles MAC addressing. Then you have the network layer, which is where Dino's Lisp is actually operating on. That's your IP layer, which is Internet Protocol. That's where you actually have the addressing space. The transport layer, I'm sure a lot of you are familiar, TCP IP. The session layer is where you handle socket connections and sessions above that. The presentation layer is where you actually have the data representation. HTML would be a form of that. Application layer is where you eventually get to your web browser. So I always use an analogy. Let's look at this stack. Now, most developers sit on the application layer. They code in JavaScript or they code in HTML, or they may even be building, applications like blockchain would be presentation, uses some session on the base layers, but most even blockchain developers don't really look down to the socket layers and the socket management. So what happens if an application guy goes down to Dino's network layer? Well, the internet would probably not work very well. And it's a very good thing to have that distinction to understand that because the lower you get, the more you deal with, right? So we can consider a blockchain in a sense a uni-layered system, as we know. We have Ethereum, which they, in a sense, kind of have two layers, where they have their actual Ethereum virtual machine blockchain layer, and then they have their Solidity compiler, which essentially compiles into their native bytecode, into the Ethereum virtual machine. So what we've done here is we've created these abstraction layers that work directly within the OSI network stack. As you can see, network services, or Lisp, is our network layer that covers the transport to the physical. Then the lower level protocol handles on the session layer. And then we get the ledger and the register and the operation and the API as the form of our presentation. And then we create a new application space with the interface and logical. So what's the necessity of layers? Essentially, a layered system, it follows natural laws. We know nature grows out in layers. You see a tree, it grows in layers. We see matter, it has certain layers of responsibility where simple protons and neutrons and electrons together form a simple atom, but then they start forming covalent hydrogen or ionic bonds, and then they start forming molecules, and then the molecules eventually can start to form tissues, and tissues form organs, and so on and so forth. So understanding the natural layers allows us to develop a system that works, because nature's worked for a long time, so it's a good model to follow. So as I was saying earlier, layers allow developers from all levels of experience to develop on the layer that is most suited to them. Generally, entry-level developers are going to be coding from such high levels of abstraction. They may even create certain things that they say, hey, I made this calendar widget or I did this, but generally they're building on code that's already been built on. Most of the web code you'll see today, CRMs, are built on massive PHP frameworks, which is yet one more abstraction layer from PHP and MySQL. So it allows people to kind of code at their specific level, which, as we've seen with smart contracts, there's certain logical errors that can happen, which generally lead to a lot of money being lost. Now, with this still being very experimental technology, we need to be very responsible with how we deploy it. So the internet as we know it on its lower layers, especially TCP/IP, IP, they all have to be standardized. If people don't have a standard connection between one another, then you end up with incompatible programs. Now, if we had an incompatible internet, then people's computers would not be able to talk to one another and it would not function. So this is where we get, because the blockchain somewhat has standards. You have ERC20 token standards, and you have, Bitcoin improvement proposals, but still, the standardization process is very behind closed doors. It's very difficult for you to actually have direct contribution. So that kind of sets the stage for what we're doing with the working groups, which are going tomorrow, which is the initial standardization process on the stack. So essentially, the next part of the stack that makes it very important is that node roles can essentially be identified between different layers so that you can actually break processing up onto each one of the layers. I always say, if a web browser had to run on a router, it wouldn't work, right? The router has a specific role. It's either forwarding packets or, as Dino said, dropping packets. You want to make sure that the router does just that. The router doesn't have to process the packet. It doesn't have to understand what's in the packet. It's pushing raw bytes. And that's what allows it to scale. Because down there, it's pushing a lot of packets. You leave the interpretation for the higher layers on the OSI. And so this is one of the fundamental qualities that's going to give us the scalability of advanced contracts. So let's look at the fundamental base, the lower level library. I guess in a nutshell, the lower level library is a polymorphic template library. What that means, polymorphism is your ability to inherit a class from a class. So good coding standard means that code can be used over and over and over again. If you write a method that slightly changes things and you only use that method once, that's not the best architecture. So the lower level library is composed of three different components: the crypto, the database, and the protocol. As you can see over here on the right, this is the lower level database in action. This was 100,000 keys writing to the LLD and Ripple's new DB, Google's level DB, and Oracle DB. For context, Oracle DB is what is used for your wallet.dat file. If you've ever noticed, wallet.dats take quite a long time to load. Oracle's DB breaks down significantly the more keys you add to it. It's a log M algorithm. Supposedly, the B tree seems to fail. I notice about 5 million, 10 million keys, you start to get a really, really high complexity. LevelDB is what was developed by Google to be a very large storage engine to handle a lot of keys, and that's the fundamental that Ethereum is built off of. As you know, Ethereum blocks take about 25 seconds to actually validate if you don't have a solid state drive that's fast enough to read it, because there's such a high data complexity to it. And of course, as you get more and more and more keys, it slows down exponentially. Ripple's new DB was a basic disk hash map table. Somebody, when I was doing these benchmarks, asked me to compare it, so I figured I'd compare it. Ripple has a bit higher scalability. As you can see, new DB is a little bit faster than LevelDB, but the LLD here takes the win. 0.81 seconds, which ended up being 536,000 writes per second, 917,000 reads per second, and then the destructor time, which is just a cache thread running in the background. So I just counted that just to be a little more fair. But essentially, overall, 0.81 seconds for the total execution time. Ripple's new DB, 7 seconds. LevelDB, 7.07 seconds. Oracle, 18.27 seconds. As you can see, significant difference. So this database being your fundamental lower layer, it doesn't matter what your architecture is above it. If you have a higher scalability on the lower layers, everything else is going to scale on top of it. So with the lower level library, the code is modular. So what this means is, this is an LLD, as you can see up at the top. You have the keychain and you have the specific keychain type. This is using what's called a binary file map, which is a specific type of keychain. But the beautiful thing about the lower level database and the lower level protocol is you can plug in any new type of processing system. So I'm actually working on a binary hash map table, which uses less memory requirements. It's a little bit slower than the binary file map. My last results are about 1.2 seconds, so it's about, a little bit slower, but it still takes the lead on the other ones, and it has no memory requirements. But what that allows developers to do is it takes the base templates that are used over and over again, you plug in new types of processing systems into it, and you always have high levels of scalability. So, as you know, the LLL is the foundation of Nexus, and it's what everything is built on top of. So naturally, we want to make sure that the limits of the lower layers do not limit the layers above it. So, we get to the network. The network is responsible for the end-to-end communication between nodes. Most people think of the network on a blockchain as the blockchain. That's not. No. The network goes very, very low, and you understand that even the way you manage your sockets determines your scalability. So in this specific one, this is the lower level protocol running. It's 194,000 requests per second. This is running, I think, a couple byte pings, some data samples, time samples between one another, and I think this is over a few thousand connections. You get such high levels of scalability on the LLP because of the way you manage the threads, the way you multi-thread, and also the way that you do asynchronous. So another part of this is we are going to have a routing complexity of order of 1 through IP multicast. As you saw with Dino and IP multicast, this is very, very important because, for one, when you have the conventional n-squared complexity routing on the network, you actually have a lot of vulnerabilities for eclipse attacking, man in the middles. When you have a multicast, that means the packet goes out and it fans and it's delivered to everybody at the same time. The difference between unicast and multicast is I'm multicasting to all of you right now. I am speaking one thing and all of you are getting it at the same time. If I were unicasting, I would have to spread a message into a message into a message, and you can see the complexity would get exponential the more and more it propagated through this room. It would become very, very slow. So multicast is very interesting because order of 1 is the holy grail of any scaling. Hash maps have order of 1 generally, which means constant time no matter the size of the data set. That's very, very important to distinguish because usually in conventional algorithms, the larger your data set, the slower everything becomes. As you see, the larger the blockchain gets, the slower the blockchain gets. And since everybody has to replicate the same data across everything, it becomes very, very cumbersome. So this order of 1 scaling on the network is going to allow more nodes joining the system to increase the efficiency, but not draw upon the load, because more nodes creates more security, but on the other side, if it's n squared, more nodes makes the routing complexity higher, which makes messages propagate slower, which then gives more reasons to not increase block sizes, and so on and so forth, and so on and so forth. So another really fun part is Lisp, Location Identity Separation Protocol, as you guys know. It decouples your address space from your actual endpoint identifier. So when I use WhatsApp, or I use Telegram, because I want my privacy, right? For one, that's a bit of an illusion because they screenshot your phone. But passing through a server, right, you don't know if that Diffie-Hellman is going between you and the server, and then a Diffie-Hellman's going between you and the other person, and they're decrypting everything in the middle. I don't know. I can't see their source code. I'm assuming that's how they do it, because you have a nasty little problem called NATs, right? Well, they're a solution and a problem. I guess for peer-to-peer, it's a problem. For everywhere else, it works great. It's called the network address translation, which means on the router, all of you guys having your devices here essentially are connected through the Wi-Fi router. Now, this whole hotel probably only has one IP address. As you know, Dino said 2 to the 32. In geek terms, that's 4.3 billion. But that means that's the maximum amount of addresses we can have. So right now, you can't listen on your device, which means I can't open a direct peer-to-peer connection to you. So I have to pass through a server that's not behind a NAT, and you have to pass to the server, and then the data has to pass through. With Lisp, it opens that up completely. As you know, there's 100,000 Bitcoin nodes, but only 10,000 are accessible. That's the reason, because it uses UPnP, which doesn't really work. So Lisp actually does NAT traversal for us, and it encrypts all of the data and packets on layer 3. Which means on the OSI, we can encrypt again on layer 5, and then have encryption on layer 3, and have direct peer-to-peer connection, which means I do a Diffie-Hellman with your device, which means we have a direct peer-to-peer connection, you don't have man-in-the-middle attacks, and you have a secure, encrypted communication system. That is one of the fundamentals that we're looking at as well, because we need to have that type of privacy, and I don't necessarily trust these private chat things that we use. So we get to the next layer. This is the ledger. So in context of the stack, the ledger manages ownership of registers. So as I was saying, like the router, it's passing packets. It's just moving data back and forth. The ledger is a similar type of thing. It is moving data, but it's proving who owns what data through the cryptographic proofs. So it's responsible of chaining the data into the immutable object. That's a fancy way of saying you can't ever change it. If you change it, you break it, right? It handles rights management of registers, which means if I write this data, I own this data. This is me. I can record whatever I want. I can record my title. I can record my deed. If you don't have some way to prove that ownership or transfer that ownership, the ledger's not really doing its job. So it's verified through the locking mechanism, through global consensus. This is, think of it as mathematical proofs that more people validate upon. This is why we want a public ledger, not a private one. I know a lot of people are saying, what's the difference? Why would I want to use a blockchain when I could use a cloud? Well, because people think that a blockchain is a storage device. It's not. It's an ownership tracking device that allows immutable ownership to be stored so that other private systems can then connect. If you want to use the cloud on that, that's fine. So the more people you have validating this, the more secure it becomes. This is very, very important to understand, because people say, well, why don't I make a private blockchain? Well, because then you got a private MySQL database. The point is not necessarily to recreate the same problems we had before, but to have new solutions. And having it as a public system really has, anybody can attack it, anybody can go to it. If you have private centralized delegated proof of stake models, right, like EOS and BitShares and whatever, you open up 0 days. Since there's a central point of authority controlling it, the central point always allows you to find a 0 day to attack and control. So, long story short, the ledger proves ownership and permissions of registers on the layer above. Registers. Now this is where we start getting fun. I don't know, for me anyway. We'll see if you guys like it. Registers are state objects. So they hold data owned by the signature chain that published it. So essentially, Bitcoin, Ethereum, all smart contracting languages are stack-based, okay? We don't use stacks. You know those old tape computers? You know, you see the CIA or the old movies like War Games and whatever? Yeah. Those are stack machines. Very, very primitive, very slow. It requires an incredible amount of operations because you're always having to push and pop from the stack in order to have that happen. So, you know, to add A plus B requires 5 to 6 operations. It works. You know, it's a decent architecture, but processors use registers because they're more efficient. Because to access a register's value is order of 1, because you know its exact index. So this is where we get into Nexus. I don't really like to call it a virtual machine because I don't think any of them are virtual machines. I guess you could call it, but it's a register-based virtual machine. Usually 30 to 40% increase in the actual processing capabilities just from using registers rather than stacks is pretty standard. I think they did that with Java. But anyway, this is not just a data storage device though, but it's where we can start tracking ownership. So registers can be transferred and they can be written, or they can be used as proofs for the operations above. Now this is really important because now not only am I recording this data, or am I transferring this data to somebody, but now I can use this data as a proof for some other event. And that becomes very, very important because then you create a chain of registers. And the ownership chain, which essentially allows you to create a series of events that bring you upon a certain result, which is what we would call a smart contract. I generally don't like to use the word smart contract because I see smartphones, and smart TVs, and you know, what else needs to be smart for us to be dumb? But anyway, I like, you know, advanced just to change the lingo a little bit and make a couple bad jokes. But object registers are predefined serialized classes that can be updated and change state through the ledger. So this basically means they're predefined, like an account would be an object register. An escrow would be an object register. A token would be an object register, right? Now this is very important because a lot of this is running into native actual bytecode on the operating system level, so it processes very quickly. When you have the blockchain and then let's say an interpreter and then a compiler and then all this stuff like you get on normal Ethereum and blockchains, every layer you go, you're slowing down more and more and more. So we like to run at the lowest layer as possible to do everything down there as possible that makes it run as quickly as possible. That's why C++ is a preferable language to code in because it compiles into native bytecode. So now we get raw state registers. That's just your own custom serialized format. It could be hello world for all you want. That's generally what you're going to use to be storing your titles, your deeds, your houses. Those are going to be standardized on higher levels. They're not going to require a low-level standardization process because they're just raw, simple bytes. They're proving a certain piece or data is published, and they're proving whatever signature chain owns this. Now, this is the really fun part, because some of you developers will understand what I mean, but registers form a relational database model. But the cool thing about it is the relations are managed by the ledger. So I create a relation with somebody else's register and some other register and some other register. This register holds state of a certain number of tokens that can be used as a proof of ownership in another register if that token owns that register. That's a mouthful, I know. But what I mean is that there's relations between all these data. And the relations between all this data is managed through the ledger and through the cryptographic proofs. So this is another part where we get a lot of the complexity and power in our advanced contracts. And this is where our architecture significantly differs from everything. Ethereum's just a little bit more of a glorified Bitcoin script engine. They added some more primitive codes, they added loops, and then they added a compiler. We have completely fundamentally changed the architecture of how we're viewing this. We'll have validation scripts, which are slightly different, but this is the core of it anyway. So registers can be chained to one another, having ownership govern across all of the chain. Now we get to operations. So operations, they're bytecode that determines the logic, and it brings a register from one state to another. So you would want an operation, let's say an op debit, and what this is going to do is that's going to change the state of your account balance. Just like the other person can use that as a temporal proof to then credit their account, as long as they have the proper proofs and the proper ownership chain to then do another state change to increase the value of their account. So operation logic is determined by interaction with each object register and the logic that follows its state change. Now this is important because operation logic needs to be standardized too. This is how we don't run into DAO problems. Because it's you get a jar of jelly beans. This is an Ernie statement. He always uses jelly beans, I don't know why. But you get a jar of jelly beans and you pass it around a room. And you have people guess how many jelly beans are in the jar. Once you get to about 200 people, you average all the guesses together, it's within 0.5% accuracy. So what this means is that the more of us together that contribute to an idea and a standard converge upon the actual truth, which is interesting, the average of it all. So this is the importance of standardization process. And this is the importance of having an open door standardization process to kind of bridge these things together so that all operation logic is sound, which means it's safe to use and it's quick to use. You don't run into extra complexities. You don't oversimplify it. You don't overcomplicate it. And you make sure that it's very, very, very secure. So the next part is validation logic. This is the programmable logic that you're going to essentially interact with. This would be op debit if time is greater than 5 years from now, which would mean that that will not validate to true until it's 5 years from now, which allows you to create certain locks or to move the funds or to set certain stipulations on the operation actually executing with the other operation using that one as a proof. Now, as I said, operations require a standardization process along with registers to define logic that is secure and efficient. Now we get to the API. This is very, very important. An API stands for Application Programming Interface. So most modern systems, they use JSON APIs for most of their systems. And they plug into one person's and another. What it basically lets you do is interact with the internals of a system. Right now, if you want to interact with a blockchain, you have to learn these complex languages, or you have to find a blockchain developer, or, if you're lucky, you find a blockchain developer, I should say, because getting to the point, for every 20 blockchain projects, there's one developer. That number is grossly out of proportion, which it creates very, very high pay. And essentially, it's really hard to learn the knowledge of a blockchain developer because the true blockchain developer gurus that make lots of money, there's a huge economic incentive not to help people learn. Why? Because they make tons of money, being the only one that knows. So the lack of developers is due to the complexity to interact with the actual system securely and to be good. That's a problem. We want to have a bountiful, evolving economic system. We want to have a lot of people that interact with it. There's a lot of businesses that all they know is like, hey, I got an ERC20 token developer, and yay, I got a token. But now what? Well, they don't know now what. There's a couple little things. We can maybe do a little state recording or data, but it's still incredibly complex to deal with it, which means that the barrier of entry is very, very high. And a lot of the people that this can really benefit all over the world aren't going to be able to interact with it. The people that have these dreams of these companies, they're going to have a hard time doing it, and they're going to have time doing it successfully. So with the API, it's going to become one more thing somebody can plug into. You're not going to have to change your whole system. You're not going to have to change the way you do things. You have one extra API that allows you to interact with the blockchain to do specific contract logic that's important. You don't want to do more than is necessary on the lower layers. You want to do that on your application layer as much as possible, and you use the ledger for what it's good for. So now we get to the application space. Now this is our new application space. Now decentralized applications, I don't like saying the word DApp, but on Nexus they'll develop their own logical and interface layers. And the logical layers will handle the implementation and interpretation of all of these API calls. What this means is your system will run. It can handle most of everything that it can off the blockchain, but it'll interact with the API when it needs to handle certain tokenization logic, certain register chaining, certain ownerships. I'll show you the demo, actually, after the next slide. That's going to show you a full stack running and full validation and showing you a really specific use case that can be used off multiples of industries. Most people see a blockchain and they use an ERC20 token, which is good, but there's a lot of fundamental things we can do with it. So that's why we need the scalable system, and that's why we need the easy to interact with system. So old systems will be very easy to integrate, and that's a very important thing, because from talking to a lot of businesses over the years, a lot of them are told that blockchain is going to take everything over, so they think they're going to have to completely get rid of everything they have and rebuild it. But we want to help them find a way to augment it, to improve it. So that's where the API and the application space are very important. So I'm about to show you a demo of Tritium in action. Now, this is live running code. This is full validation on the ledger, register, and operations. This is showing all the cryptographic proofs. This is running them in real time. I actually set it up as a simple little demo where I'm going to press enter because it's going to execute one transaction at a time every time I press enter. But it's going to show you how tokens be utilized in many different processes, including their utility. Right now, there's not much utility for them. There's just store value, transfer value. But I see a really important distinguishing is tokenized ownership or tokenized assets or tokenized data, whatever we want to call it. What this means is that a token can split the ownership and the rights between many different people. And it's as easy as transferring the token to change that. You can split the revenue streams of your company. You can do stocks. But I'll get to all those specific things later, and I'll show it to you in real time. Now, this is live code running. I feel the need to express that just so that you understand. It's been a lot in the making to get going, so I'm happy to be able to share it with you today. It uses register proofs, debits, credits, writes, reads, and ownership proof through 2 signature chains. So these are complete live Tritium functions running. Now, if you'd like to be a part and see the code, we're going to be going over that in the worker groups tomorrow, and we're going to be going through the standardization process, which is going to start with a simple explanation of what everything's happening, and then it's going to really start driving into exactly what operations we're going to do, defining the logic, defining the object registers, because this is going to become a yearly occurrence. And this is going to be kind of like the IETF is for blockchain, since we're essentially creating abstraction layers on the internet to make the internet a safer place. We're going to need to make sure that these lower level things are vetted through many different people, and that we have these standards and these drafts and this openness moving forward so that anybody can interact with this specific technology at any level. Here we go. So as you can see here, this is our first signature chain. So this may look like a bunch of random letters and numbers, but trust me, it's something that's actually pretty amazing, at least for me. I love how it kind of came together. So this right here is a simple Tritium transaction. Now, as you can see, you have the previous transaction as zeros. That's signifying that this is the actual genesis. You have your timestamp, and then you have your next hash, as you guys know from the specs of the Tritium paper. So this next hash is what is able to be claimed, and the next key in the signature chain. And then we have our public key, and then we have our actual signature, and then we have the hash of the specific transaction. Now, as you see, ledger data is 0, right? Because there's no ledger data. Ledger data is what's passed from the ledger up into the register operations layer. And that's where we get multi-tier processing, because as you know, we have the L1, L2, and L3 locks. L1s are essentially going to be doing the cryptographic proving, which based on my calculations and my recent benchmarks running full lower level library validation, it was 4,800 transactions per second on one state channel. So we'll probably want to limit the data. The LOD was writing about 1.8 megabytes a second. It was a lot, very fast. Processing 4,800 actual 512-bit ECDSA operations per second as well. And then the LOP was doing another 20, 30, 40,000 requests per second on top of that, just to kind of simulate message propagation of other things other than just transactions. So anyhow, I didn't run this over the network because I figured this would be a lot easier for you guys to see and understand. As you can see up here, we got our binary file map keychain, file map 000. This is essentially handling the specific keys and showing the data size and our first transaction. So let's move to the next transaction. So right here, this is creating an account. Now, for the sake of time, I didn't give you a million transactions to show you how the state of the account has to be created, so I just preloaded this with 15 tokens of identifier 105. In this specific use case, identifier 105 is going to be the Nexus native token. Now, you see signature chain 557 is the same one up here. Now, you see ledger data, right? Ledger data was actually serialized in and then executed by the operations layer. As you can see at the bottom, now we have the account that's actually dumped to the console so that it shows people exactly what's happening. This is just kind of deserializing the specific register operation that executed. Now, this is important because, as I was saying, the L1, L2, and L3s, before I got on a little bit of a tangent, the L2s are going to process a lot of the ledger data, which means you're splitting the processing up. Now, the operations are going to be the quickest to process. The actual L1 is the slowest because the ECDSA verify is very high complexity. And that's going to be the bottleneck, which is where the L1 state channels are going to be important to parallelize that and then transfer that into a different set of signatures that pass on to the next layer, and then all the operations and registers execute. And then they leave that in a commitment message so that when the block lock comes around on the L3, it executes. So there's a simple account creation. As you can see, the hash genesis is showing the ownership, and this is 5672AE, as you can see right here. It's generated here, and that's the same one as there, because this hash genesis is what's used to prove your ownership of it. Now you can see the previous transaction hash, DAF, and that is the hash up here, DAF 40508, if I could reach it, right there. Anyway, so this is showing a basic signature chain. So now we're going to create another genesis, because we need to have two signature chains interact with one another. This is important, because this is showing how two signature chains are essentially creating register chains, and they're creating tokenized ownership. And I'm going to show you a specific use case. This one deals with music. As you know, I love music. I think music is something that's going to really help. And I think that bringing music in to the industry is how we're going to really reach the masses, because crypto's still geeky. Nobody really knows. People, have to double check transactions before they send it, and afraid of losing money, and got to have hardware wallets to keep your private keys, and we've got a long way to go. But I think music is a way that we're going to really be able to reach people and show them practical uses of blockchain. Why do I like blockchain? Cryptocurrency? Yeah, maybe. That's the incentive mechanism to build it. But hey, when I listen to Spotify, I'm using Nexus. What is Nexus? I don't know. I think there's a cryptocurrency in there. But there's a lot of cases. Anyway, we're creating a Next account. This is another identifier of 105. Now this is with our new signature chain, as you can see here. So we'll just use the last two, 109222, and we have our hash genesis again right here. And as you can see, 109022. But this is our next transaction. So now we have two accounts with identifier 105. So one important thing to distinguish is the Nexus native token is going to transfer just as quickly as any other native token that you create. All you do is you change the identifier number, and it takes two operations for it to happen. You don't have any more complexity than that. What that means to you guys is less cycles are required on your computer, which means it's going to run really, really, really fast. So what I'm doing here is I'm showing a simple debit from the initial transaction from the signature chain 08E, right, of balance 100. And then I'm going to pull a credit, which is crediting to the other signature chains. So you see 55 Nexus was now credited into there. Now the importance of debit credits is it's similar to a bank account. You see your debits and you see your credits, but the other important distinction is you'll never lose funds again. Because, that's an important thing for us to have. Because if I can send to an invalid key, and it's gone forever, and then I have to double check it, and then we have to, read the first three and the last three letters, that's not going to really be good for people. I mean, people lose their passwords all the time. I mean, come on, give them private keys. Uh-oh. So this is important because the credit has to be claimed from the debit. Now, you'll see how the debits and credits don't just work for single transactions. This is just an account-to-account transaction. I'm using two operations. So what it basically does is the creditor is signing off on their signature chain, making a signature in another transaction to verify that they are the owner of that account. So if you had a validation script on this first debit and you said expires or, only if valid if less than 1 week or less than 1 day, then you're only going to be able to credit it because that's going to value to true within that 1 day. If it's not within that 1 day, the debit goes back to you, and you credit back to yourself, which basically means you don't ever lose the money. You don't ever have limbo. This is where we start getting into fun how escrows, and I'll talk about the exchanging a little bit later too. Anyway, so now we're going to create a token. We're going to call it art. We're just giving an identifier number 22, and we're creating 100 art max supply. So this is being created by the signature chain 5572, and blah, 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 blah. That's a 512-bit hash, or 256, sorry. But as you can see, we set 6 digits, 6 significant figures. We set a money supply. We have versioning in there because we're going to probably augment the version of these through standardization processes and say, okay, well, we want our native tokens to have support for this and that and that and this. And then we go and say, everybody, yeah, we agree. Okay, let's move the draft forward. And then, after much deliberation, we'll get to a new standard. So the versioning is very important. So why did I create a token? You're going to see in a minute. Because I'm going to publish some metadata. Now, this is called a song. Let's call it art, album, greatest, like every greatest album. But anyway, as you can see, more ledger data, which is publishing this. But the important distinguishing is this was created by the signature chain, but under the scenes, this specific metadata is owned by that token. Now, what does that mean? Well, that means now the token governs this data, not just one person and their signature chain, which means that we can start using temporal proofs in order to prove certain ownerships in the supply. So what we're going to show here is we're going to show a royalties payment. Because, as you know, especially in music and just about anything, getting money to somebody is really tough because middlemen try to take it all the way through. Splitting up money is even harder because, how do I know if somebody paid me the right amount, and I got to go through the paper, and then they say this, and then I got to take them to court, and it's just big and messy and slow. So what we're going to do is we're going to create one signature chain with 50 of the tokens and one with 50 of the tokens, which means each one of these tokens represents ownership in that metadata. So now 50%, 50%. Now that's important to distinguish because any sort of movement or change in that metadata has to be proven by token holders. Now the beautiful thing is the ledger doesn't need to know that until later down the chain unless you use it as your temporal proof. So there's really not a whole lot going on here as far as the complexity of it. There's maybe about 5 database writes. As you saw, the LLD does about 567,000 writes per second. So, theoretically, one state channel could handle, 100,000 operations per second. I haven't run these operations in benchmarks, but from the lower level library tests, it seems very promising. So this is going to create us a very high scalability and a very easy to use interaction. So what I'm going to do with these is I'm going to debit some native Nexus directly into this copyright token, art, or song greatest. Now, what this means is that this debit is sitting here waiting to be claimed. So that now with these tokens here, I use the tokens as a temporal proof to claim 50% of that credit, as you can see here. Now, just to show you a little security feature, I'm going to try to double spend, and it's going to fail because the proof has already been spent. The proof has already been utilized because I used a state proof of the state of one of my object registers. Now, this object register having 50 tokens, there being 100 total tokens, I was able to credit 10 Nexus into my account as a 50% split from that tokenized data. Now, this is very important for music because you can have real-time licensing going out, especially with the Music Modernization Act. You're going to have somebody debit or pay a license fee once a month. Now, all you have to do is disperse tokens to whoever owns it, and artists, too, will be able to trade these tokens. Now, this is important because all these tokens are absolutely transferable, but they're also used as proofs. So if an artist wants to start a crowdfund, they can create a new album and release 20% of their tokens to the actual public, and those tokens can be sold on an exchange, traded, speculated on, and be used as a royalty ownership rights. So that means you're not just trading on token speculation anymore. These tokens have actual value. They have actual things backing them, and they have actual money that can be used for them. So, So we're going to do the other side now. Now this other user is able to claim their state proof, 50% from the token art, right? They're crediting it to their account because their account was using the proof. Now, as you can see, this is all proven and done in this ledger data. It's all essentially serialized into bytecode. And the bytecode is interpreted through the operations engine. As you see, it's the method called execute. And then we're going to do another double spend attempt right here just to show that the temporal proofs work. And this one tries to spend the same credit. It fails because the credit was the exact one. So this is really, really important, though, because people talk about tokens, right? Transferable tokens. Now, what's the use of a token? Well, right now, you can run an ICO. Now, that's about it. Some people talk about it, they speculate it. You hear people say, I want to know, I want to use this for royalties. Oh, we're going to make a royalties platform, or we're going to help these people do this, or whatever. But it's so far beyond that, because tokenized data allows tokenized ownership. Tokenized ownership means you have proof of many different events that happen. So what is the good use of this? Joint ownership and patent leasing, for one, which means you have a group of inventors that invent something. They create however many tokens they want. They give however many tokens to their investors. You don't need any legal paperwork. You don't need any courts, because crypto is the court. You have the tokens. You prove you own them. You claim your percent of the dividends. That could be sales, right? As far as, let's say, a joint payment. If I own a house with somebody, you can have 50 tokens, 500 tokens, 500 tokens. You can also do automatic budget allocation for revenue streams, because as you saw, that was a licensing revenue stream. So, I mean, how many business owners know how much money they have to spend just managing people and having their controllers, making sure they spend the money right or send it to the right places and the accounts and move the money and yada, yada. It's messy. So with this, you can have budget allocation based on revenue and creating layers of tokenized accounts, right? Because you can have your first input, which then goes into a tokenized account, which is your outer tier, that then goes to all the different departments that then have their own that disperse and their own that disperse. And it's easy as the token owner to transfer 5 tokens to another person to represent a certain percentage in those dividends, or transfer them back and move it around. Clears instantly. And then revenue streams adjust accordingly. So another one is the licensing and the use of copyrights for songs. Very, very important, because artists have a hard time getting their money. It's very, very, very difficult because there's so many middlemen. What this does is it makes it instant right between them. We also have tokens that can represent shares in a company. Some people have talked about this. Dividends are, paid quarterly, yearly, whatever. This way, you actually allocate a certain percentage to the token holders of the revenue that they get, and it automatically disperses, which creates higher confidence in the token holders. It removes the need for dealing with so many courts, removes the need for intermediaries, governments, and allows us to just create things that are great. So, joint ownership in properties for buying and selling. This could be joint ownership in a car, or very importantly, you could have a car dealership and then a car manufacturer do a token split between each one of them, and the token split has an account that the lease is paid in from the owner of it, and then every time the lease is paid, it distributes directly to both, and the money clears instantly. Now, another really important one is for nonprofit donation distribution, to prevent internal embezzlement and nonprofit managerial costs. As we know, about 10 to 15% of nonprofit revenue goes to the actual nonprofit mission. About 85% is absorbed in God knows what. So in this way, I've never really donated too much to nonprofits, because I don't believe they actually go to help the people that I really want to help them. So I usually just go direct peer-to-peer to those people. So what you can do in this case is, let's say 20% of the tokens go to the actual internal revenue or managerial costs, and then those 80% of the tokens, which could be 80 tokens, could be 800, it depends on how you verify it, will be able to be given accordingly to all the people that need them, and any donation automatically disperses to all. So that's another really important use case. I'm sure there's going to be an incredible more. This is just a short list. So what's in our future? What's in the future of Nexus? Well, for one, as you've just seen here in this demonstration, tokens that carry genuine utility and practical real-world applications. Another one, distributed autonomous organizations. As you know, tokens represent your ability to prove certain things, which means I'm proving my percentage ownership in whatever, which means, token votes, DAOs. You can have budget allocation. You can have credits require token proofs from everybody else. That's where you get the true use of a DAO. And then we don't need all this over-complex, hackable code like we've seen. Anyway, decentralized exchanges for all tokens. Yes, this is my favorite. Well, because, we all don't like centralized exchanges. Now, how does this work? Debit, debit, credit, credit. I put up an order on Nexus, which is an exchange object. Then I put up and I say I will debit 10 Nexus for 50 art. And then what happens is somebody with 50 art debits those 50 art into the same contract. Contract locks, it executes, and now I can credit his art and he can credit my Nexus. There you go, you have a decentralized exchange. Now, thank you. Supply chains and arbitration triangles. Obviously, supply chains, Very useful. State record, money moves between each level of the supply chain. Arbitration triangles is a really fun 2/3 multisig, which means you have buyer, seller, and arbiter. Now, this is very important because the arbiter can be your shipping company to resolve dispute between the buyer and seller in case there is one, but it always gives the buyer and the seller the ability to control their ability to settle dispute themselves. And the arbiter only has power when there's a disagreement. Since it's 2/3, that's where that type of magic happens. The next one would be fraud prevention systems. By having more transparency, by having tokenized revenue streams, by having actual knowledge of the movement of funds and availability to see exactly where everything's moving, we can reduce the use of fraud. And then obviously identity and reputation systems. As you know, we have a baseline reputation system right now for the proof of stake that's going to continue to advance, especially as we get more and more data on these tokens. So the last thing that I'd like to show is a nice video. And this video is going to show exactly what Tritium is looking like these days. And that is my cue for the guys in the back to play it. Thank you very much, everybody. You've got a bright future.
Come see what we're doing at nexusearth.com.